Okay. So all this process like chemical reduction or the precipitation, co-precipitation, etc. Again, we'll be seeing some other techniques called hydrothermal method and Sardile process. All these things produce composite in the form of kind of powder form. Okay, it's not that kind of solid thin film or kind of maybe in the form of like deposited like coating based substrate extra. No, you will not get it. You'll get in the form of powder form like nanoparticles or the composite. Okay. Say for example, if you take reagent one, only of reagent one, maybe based on precursors of calcium, so you'll get calcium based nanoparticles. But yeah, if you take some other, I mean, metal oxide based precursors, you will have a combination of two different metal oxides. That's called composites. Okay. So so the basic concept, like you'll be taking the precursors of reagents, and then that undergoes, various types of reactions like reductions as well as some maybe of some condensation, etc. At different temperature, pressures, etc. And then you get a product and byproduct. Okay, and when the reaction same like nucleations and growth like so the time and temperature and the concentration that plays very important. Okay, so it's not that always you keep a particular temperature and then throughout the reactions you keep the same time, I mean the pressure, etc. So you will not get those kind of uniform particle, reduced particle size or kind of uniform geometry of your materials. Okay, so all these things are playing. Once the nucleation started, so if you have like a heterogeneous nucleations, then probably you'll have to increase the temperature or the pressures to make sure that you are catalyzing that reaction, and then you're getting those, kind of controlled crystal or the nanoparticles. Okay. So this is one of the examples for precipitation method for the preparation of hydroxyapatite. You can see here they have taken calcium nitrate and diammonium hydrogen phosphate based precursors as a precursors for calcium and phosphorus, okay, or phosphate. And then yeah, they have also taken the ammonia to maintain those certain pH, etc. So what they did, first they dissolved those precursors in the aqueous solutions, like individually, like phosphate precursors are dissolved in the aqueous solutions as well as the calcium precursors. Okay, and again they added these phosphate precursors into the calcium precursors by drop by additions, and that was maintained at a pH of 11 by the addition of ammonium, and that was aged up to 4 hours at 80 degrees Celsius. Again, you see here at 100 degrees Celsius for 2 hours. So there the things started like nucleation. Once it is started again, the growth and their subsequent, the crystal development. All those things will be, catalyzed with the help of increasing the temperatures. Again, that was aged for 50 hours for 90 degrees Celsius, and followed by that, the calcination at 400 degrees Celsius was. So, and you can also see in the scheme like a PPG and beta cyclodextran. So that is another one concept. Like if you add some surfactant, polymer based surfactant, you can play around their nanoparticle morphology, etc., as well as the crystal growth. Okay. So because if you see the charges in beta cyclodextran as well as their structures, like they have got a conon, kind of hollow structures. Okay, and PPG has a different charges, and those all those charges as well as their structures plays an important role during the nanoparticles. Crystal development. Okay. So this morphology you can see our paper, some of my papers maybe. Yeah, this paper. Open here also. So now you can see here, this here we have used a beta cyclodextrin based surfactant to have those different morphologies. You can see here the aspect ratio of the nanorod was significantly increased when you add those polymeric surfactant. And of course, the crystallinity was also pretty much good. I mean, you can also see the number of planes which was significantly, visible in case of polymer-based, surfactant assisted synthesis method. And yeah, again, when we use again those kind of like sonochemical method, if you put those kind of ultrasonic gun again, that again produce meticulously the mesoporous structures inside the nanorod. Okay, so which was not pronounced in case of without beta cyclodextrans. Okay. So these are the few things where you can play around with their surfactant and their structures. So here the mechanism was that like kind of mixed hypothesis, like structure also plays a role because it has got a hollow structures. Once the polymers, that beta cyclodextran, when you are dissolving it inside that precursor solution, what's happening? The crystal starts to form around that cone or the hollow structures. And then once you do the calcination, the template, the beta cyclodextran, they will start to decompose. As a result, that void will start to form. Okay, and the another mechanism what I was discussing with you guys, like bubble formation. So you can, with the help of those mixed, method like 2 minutes, 2 second on and 1 second off, can play around those, heat transport, heat transfer, issues. Okay. So once the bubbles form, then moment when you switch off those 1 second of those ultrasonic gun, the bubbles, will get broken and that voids will be, occupied, presence in your nanomaterials or nanorods. Okay. So yeah, those are the few, key role played by this kind of polymeric based surfactant. So now the next method, yeah, we do have other methods like hydrothermal and salvothermal synthesis. Almost both are same. The way the carried out the process in the kind of container or kind of some vessel, etc. The only difference is that hydrothermal means you are going to dissolve all your precursors, or the total reaction usually happened in aqueous media, okay, or the solutions. But in case of salvothermal means your chemical process as well as how the dissolving of your precursors will be happen in the non-aqueous solutions. Okay, so it's a method of crystallizing substances from high temperature aqueous solutions at high pressures, or preparation of nano particles from high temperature aqueous solutions at high vapor pressures. Okay, and the total reaction or the crystal growth usually performed in an apparatus which is consisting of stainless steel pressure vessel called autoclave based process, and usually the precursors are dissolved in the suitable solvent or the aqueous media, and then will be pouring into the autoclave molding, and which will be under very high pressure as well as high temperature. And then the reaction get initiated with the help of high pressure. Okay, which is called hydrothermal method. And if you use some organic solvent, kind of some solvent like a THF or some toluene, etc., that is called salvo thermal reaction. So this is how the autoclave molding or the hydrothermal process machine, that vessel looks like this. You have a multiple liner, just like a furnace, how you used to do those metal based castings. Like we have a different layer, like Teflon liner, and then stainless steel autoclave, and then stainless steel lid, etc. Okay, to make sure that the energy is not getting wasted. That means heat energy, whatever the pressure as well as the temperature they are supplying, which is not going to be come out at all. Or there'll be no the changes in the energy. So since everything is very closed condition, the environment, the results will be pretty much homogeneous. That means the particle size or the kind of distribution will be very uniform, And the morphology also, like it is going to be very controlled way, because the pressure is, or the temperature, I mean the heat is going to be uniform throughout this container. Okay, unlike the precipitation method, you are going to do all these things with maybe in beaker or some sort of like the vessels which are opened way. Okay, that means there will be changes in the energy, heat energy, or some sort of pressures, etc. So as a result, the crystal growth will not be that much uniform throughout your materials. Yeah, that's the strength of this process. Like it's a one-step process, of course, and it minimizes a lot of energy consumption. And since it is a closed system, it doesn't I mean, do any harm things to the environment. And of course, you get very homogeneous. I mean, in nature. I mean, in case of particle size or the morphology, etc. So that's it about those salvo thermal or the hydrothermal method. And then we do have one more process called Sardile Approach. Okay. And this also you get a powder form nanomaterial or the composite product. And once you get this, maybe you can take it to again hot extrusion or the sintering process or compaction, etc., to make whatever the solid product you would like to have it. Okay. Yeah, Sardile process also kind of, producing some nanoparticles by formation of an oxide network through the reactions called maybe of condensation or the hydrolysis reactions. Okay. So what is solvent gel, first of all? Any idea what is solvent gel? Sol means you are taking some material and then you are dissolving it in a suitable solvent. Okay. That means completely transparent. Okay. Gel means you are taking some material and then you are dissolving it, and it is not going to be like a transparent. Rather transparent, it forms opaque or some sort of slightly higher viscous material. That means some network is happening between the material and the solvent, or the other material what you have taken, or the solvent, which is called gel actually. That means salt is completely dissolvable, and gel means which is, once the gel is formed, you cannot dissolve at all. Okay, just like a thermoset polymers. So salt is a stable dispersion of colloidal particles or the polymers in a solvent. Okay, and gel means it consisting of a three-dimensional network which contains a liquid phase. Okay, so what usually do in the soluble process? The process involves conversion of monomers, that means macromolecules, sorry, monomers or the organic molecules, into the colloidal solutions. First the salt will form, and that act as a precursors for the integrated network formation of gel of either discrete particles or the network polymers. Okay. And in this chemical procedure, first salt, the colloidal solution is formed, and gradually it evolves towards the formation of gel-like basic system or the morphology. It's containing both the liquid phase and as well as the solid phase. And their morphologies are again ranges from discrete particles to any kind of network. Okay. And in the case of colloid, the volume fraction of particles may be so low that a significant amount of fluid may need to be removed initially for the gel-like particles. Okay, so once the gel is formed, and then with the help of different drying process like a supercritical conditions, etc. Okay, or maybe of using centrifuge or semi-bendation process, you can obtain different types of component like. So you have precursor solution like kind of some precursor, and then you're dissolving it either in aqueous solution or some solvent, and then that undergoes for hydrolysis or the condensation reaction, and then you get the increased viscosity, which is nothing but gel formation. Okay. Once the gel is formation, again, whatever those remain, those liquid presence in the gel, we have to take it out by using a different drying process. If you use some critical drying process, you get a aerogel, and then just like drying it in oven, you get a aerogels. Okay? And yeah, so the next topic would be hydrogels. Before getting hydrogel, we'll see some of the case studies tomorrow, like how the gas barrier properties are improved when you take two-dimensional nanocomposite or kind of one-dimensional nanocomposite. What are those differences, etc. You can start now also. You have time, right? Yeah, here. So nano clay. Have you ever come across this word nano clay? Clay must be knowing, right? But nano clay may be a new word. It's nothing but nano clay is nothing but I mean it's a combination of different metal oxides, and by I mean considering their like elements like alumina, silica, etc. They have been divided into different categories. Okay, so we'll see the basics of nano clay and various types of nano composites, and then I'll introduce this nano clay for different applications and their some unique characteristics of the properties. So clay or the nanoclay, which is comprising of aluminum silicate layers separated by a few nanometers. Okay, I mean kind of hydrogen bond or the van der Waals forces. Okay, usually if you see the clay structures, like I mean they have got a kind of TOT structure. That means you have a tetrahedral sheet and octahedral sheet, and maybe a sandwich of like a TOT. I mean tetrahedral, octahedral, and tetrahedral. So eventually you will have only two different types of nanoclay. One is 1:1. That means one tetrahedral sheet, and under that you have a octahedral sheet. Okay, and tetrahedral may be of silicon, and octahedral may be of aluminum and titanium, extra, so on, so on, so. And we do have a 2:1. That means sandwich structures. Okay, tetrahedral and then octahedral, again a tetrahedral kind of I mean structures. Okay. And by considering those ratio, I mean TOD ratio, you have a like kind of 1:1 type, only one type of clay, which is nothing but kyanite, and then you have a two type, I mean having three different types like a tog or pyrophilite and illite or smithsite, etc. Again, the clays are again divided into some other types, like by I mean looking at their morphologies, like a tubular structure or kind of hollow architecture and channel type, as well as some three disc based fluid types. Okay. So this table will give you the broad picture about those different types and their chemical functional, I mean, composition and the distance between the two layers, etc. Okay, and then cation exchange capacity and their morphology. Like if it is nanotube, how much the diameter or the length, etc. And if it is something like a disc, how much the diameter and their thickness, etc. All those things. Okay. Leponite, which is nothing but three-dimensional 2:1 type of nanoclay. Yeah, you can see some of the transmission electron microscope halo set tube, which is 2:1 ratio. You can see the halo tube. Okay, you have one halo tube which is center. I mean the space is vacant. Okay, and this is one of the clay martmellonite. You can see the I mean the different layers of clay layer, and which are separated by the few nanometers. Okay. Again, you have a sepiolate needle. You can see pretty much, I mean, high aspect ratio. And then you have a leponite disc, which are three-dimensional in the form. You can see the disc type of, I mean, morphologies. So if you see the nanocomposite dispersion mechanism, like we have a three different kind of, I mean, dispersion. One is intercalation. That means you have a clay layers, and then you are introducing some matrix, maybe of metal or polymers, etc. And moment when you introduce the matrix, what will happen? They will try to, I mean, get into that space between the two layers. Okay. As a result, this space will start to increase. Okay. That is called intercalation. Okay. And sometime what will happen? That each, I mean, clay layers will not be increased actually. Okay. Rather, each, I mean, individual layer increment uh, kind of like two, three layers combined together, and then there will be a huge gap. Okay. So likewise, there will be a morphology. I mean, the nanocomposite I mean, dispersion will happen. That is called maybe intercalation as well as the flocculation based concept. Exfoliation means all the layers get exfoliated. I mean, kind of delaminated completely. That means there is no, I mean, kind of layers which are connected, I mean, together, like a number of layers, three layer, two layer. So you can see all the layers are completely delaminated and which are dispersed individually, okay, which is called exfoliation. So now Now, this I quite often I used to discuss what is surface modification, etc. Say, for example, clay is completely hydrophilic, and if you see the space between the layers, they are roughly of 2 to 10 nanometer distances. And in that small gap, if you want to insert your, polymer chains, which is pretty tough actually. So slightly before introducing the matrix, if we can increase that space between the layers and slightly like kind of 50 nanometer or some 100 nanometer, and that will be beneficial or that will be easy for introducing polymer chains between the clay layers, right? So that is what like a quantity of surface modification, what really matters when it comes to the nano clay. Say, for example, you see clay layers, and then they're introducing some organic molecules, which are red color. Okay. So if they introduce the organic molecules like very larger chains or some sort of larger molecules, you can see how much the clay layer is getting increased. Okay. So once the clay layers, distance between the layer is getting increased significantly. Okay. Then, then thereafter you take these polymers for the preparation of nanocomposite. Then you can introduce polymer chains very easily between the clay layers. Okay. As a result, what will happen? You can easily exfoliate this, nano clay. So once you do the exfoliation, you will have a very good properties. Of course, because the dispersion is very good. As a result, once the dispersion and the distribution is good, you'll have improved technical properties. Now you're gonna see some of the specific properties. You can ask me that intercalation. We have three different mechanisms, and why to prefer exfoliation something. It's not that exfoliation is better for certain properties and intercalation is better for certain properties. Now we're gonna see that. So now, so we have prepared some polymer based composite, and we are targeting for some barrier properties. Barrier properties, maybe you can say example for tire. Okay. So tire which has high pressure and it runs for, quite long time. If you have this kind of pure matrix which has no nanoclay, what will happen once the gases, if the gas wants to come out or if you want to penetrate the gas, you can penetrate very easily because they have a high amount of randomness. Okay. But if you have the nanoclay which are intercalated morphology, you have a nanoclay, this kind of intercalated structures. Though, so the gas needs long time to, penetrate the composite structure and then it can travel to the other side of the sample or the product. Okay. Because it cannot really diffuse into this inorganic nanoclay, right? Because inorganic nanoclay is highly dense as well as they are crystalline in nature. As a result, there is no void or gap where the gas can easily diffuse into that. So as a result, they'll start to find the path through this matrix, which is nothing but polymer or the rubber. Okay. So if you see, if you have this kind of intercalated morphology, you will have a better barrier properties. But if you have the exfoliation, you're going to have a less barrier properties. Okay. But if you want to have the mechanical strength like modulus or something, you should have the exfoliated structure because exfoliated will give you the uniform dispersion. But rather intercalation gives you the, some oriented structures where the clay layers are slightly, the distance is slightly increased and then it got, dispersed. Okay. Okay, so now I'm not discussing about drug release because I did not teach you guys what is drug release and their basics. So this we will discuss later on. Yeah. So if you have any doubt, we can discuss about this clay concept or some other, the hydrothermal or the Sardile process. For the midsum, till tomorrow, what I'm going to teach you, maybe till the hydrogel part. Yeah. Okay, then if you have no question, see you tomorrow then. Hmm?